Rocket science is more than a field of study, it's a gateway to the cosmos. From launching satellites to sending humans to Mars, rocket science is behind these daring ventures. But what if we could revolutionize how rockets are propelled? Enter a new propulsion system that merges arc flash, microwaves, and magnetic fields. Traditional rocket engines rely on chemical reactions, which have limitations in efficiency and sustainability. Scientists are always searching for new ways to overcome these challenges. One promising avenue is the combination of arc flash, microwaves, and magnetic fields. Imagine a rocket that doesn't rely on explosive fuels, but uses advanced physics to generate thrust. This could lead to safer, more efficient, and more sustainable space missions. In this essay, we will delve into this groundbreaking propulsion system and explore its potential impact on the future of aerospace technology. Buckle up for a fascinating journey into the future of rocket propulsion. The propulsion system we're discussing is unlike any we've seen before. It combines three advanced technologies: arc flash, microwaves, and magnetic fields. Arc flash is a sudden burst of electrical energy used to ionize gases, creating plasma. Plasma, the fourth state of matter, consists of charged particles that can be manipulated by electric and magnetic fields. Microwaves, a type of electromagnetic radiation, transfer energy to particles efficiently. In our propulsion system, they heat the plasma further, increasing its energy and velocity. Magnetic fields exert force on charged particles, directing the flow of plasma. By carefully controlling magnetic fields, we can generate thrust in a specific direction, propelling the rocket forward. Together, these components form a powerful and efficient propulsion system. It's like combining the best elements of electric and plasma propulsion technologies. The result is a system that could dramatically improve the performance of rockets. This novel approach could transform our approach to space travel. Arc flash is a critical element in our propulsion system. It begins with a high-voltage electrical discharge between two electrodes, ionizing the gas and turning it into plasma. Plasma is highly conductive and can be influenced by electric and magnetic fields. When an arc flash occurs, it creates a stream of plasma that can be controlled and accelerated. The process starts with a power source, such as a battery or capacitor, that stores electrical energy. When activated, the stored energy is released between the electrodes, generating plasma. This plasma is then ready to be manipulated by microwaves and magnetic fields. One key advantage of using arc flash is its efficiency, relying on electrical energy rather than large amounts of fuel. This makes it a more sustainable option for rocket propulsion. Additionally, the intensity of the arc flash can be adjusted, providing precise control over the amount of plasma produced. Overall, arc flash is the foundation of our novel propulsion system. It provides the initial burst of energy needed to create plasma, setting the stage for the next steps in the process. Microwaves play a pivotal role in our propulsion system. Once the plasma is generated by the arc flash, microwaves are used to heat it further. Microwaves are a form of electromagnetic radiation that can penetrate materials and transfer energy to particles. In the context of our propulsion system, microwaves are directed into the plasma chamber. Here, they interact with the charged particles in the plasma, increasing their energy and velocity. The use of microwaves is advantageous for several reasons. They can heat the plasma uniformly, ensuring that all particles gain energy. This uniform heating is crucial for maintaining a stable and efficient propulsion system. Microwaves are highly controllable, allowing us to fine-tune the heating process. Microwaves can transfer energy to plasma particles with minimal losses, converting most of the input energy into kinetic energy. This high efficiency is essential for long-duration space missions where energy conservation is critical. In summary, microwaves are a key component of our propulsion system, providing the necessary energy to accelerate the plasma and enhance the overall thrust. Magnetic fields are the final piece of the puzzle in our propulsion system. They direct and accelerate the plasma, generating thrust. Magnetic fields exert force on charged particles. This allows us to control the plasma flow, providing precise control and efficiency to generate thrust. The experimental setup for our propulsion system is both complex and fascinating. It involves several key components, each playing a crucial role. First, a high-capacity battery or capacitors provide the electrical energy. This energy is directed to electrodes in a gas-filled chamber. A high-voltage discharge generates plasma. Microwaves are then directed into the plasma chamber. Electromagnets manipulate the plasma flow. Finally, sensors and cameras monitor the plasma. The methodology for testing our propulsion system is carefully designed to ensure accurate and reliable results. Each step is crucial for understanding how the system performs and identifying areas for improvement. First, we prepare the experimental setup, ensuring that all components are properly installed and connected. The power source is charged, the microwave generator is calibrated, and the magnetic field system is configured. Safety checks are conducted to prevent any potential hazards. Next, we initiate the arc flash, generating plasma. The intensity of the arc flash is carefully controlled to produce the desired amount of plasma. Once the plasma is generated, we activate the microwave generator, directing microwaves into the plasma chamber to heat the plasma particles. We monitor the temperature and velocity of the plasma to ensure it reaches the required energy levels. Finally, we manipulate the magnetic fields, adjusting the current flowing through the electromagnets to direct the plasma flow. Sensors and cameras capture data on the movement and acceleration of the plasma. This information is analyzed to evaluate the performance of the propulsion system. The results of our experiments with the novel propulsion system have been promising. We observed several key reactions and measurements that indicate the potential of this technology. Firstly, the generation of plasma through arc flash was successful, producing a stable stream of plasma with consistent properties. When microwaves were introduced, the plasma particles showed a significant increase in energy. The temperature of the plasma rose and the particles' velocity increased, confirming that microwaves are effective at heating and energizing the plasma. The manipulation of plasma using magnetic fields also yielded positive results. We were able to direct the plasma flow with high precision, generating thrust in the desired direction. The acceleration of plasma particles was measured, and the data indicated efficient energy transfer from the magnetic fields to the plasma. Overall, the observed results demonstrate the viability of the propulsion system. These findings provide a strong foundation for further development and optimization of the technology. Despite promising results, our propulsion system faced several challenges. Addressing these challenges is crucial for advancing the technology. One major challenge was maintaining stable plasma. We experimented with different gases and electrode materials. Controlling microwave energy was also critical. We redesigned waveguides to prevent leakage. Manipulating magnetic fields required sophisticated designs. We improved magnetic field uniformity and plasma interaction. These advancements are crucial for future propulsion development. The successful development of this propulsion system could have profound implications for aerospace technology. It opens up new possibilities for space exploration and satellite deployment. Firstly, the increased efficiency of the propulsion system could reduce the cost of space missions. Traditional rocket engines require large amounts of fuel, which is expensive and heavy. Our system, relying on electrical energy, could significantly lower fuel costs and increase payload capacities. This could make space missions more economically viable. Secondly, the sustainability of the propulsion system is a major advantage. The use of electrical energy and plasma reduces the environmental impact of rocket launches. This aligns with the growing emphasis on sustainability in all fields of technology. Furthermore, the precision and control offered by our system could enhance the maneuverability of spacecraft. The ability to precisely control thrust allows for more accurate positioning and navigation, improving the success of these missions. In conclusion, the future implications of this propulsion system are vast, potentially revolutionizing aerospace technology and paving the way for new explorations. The combination of arc flash microwaves and magnetic fields in our novel propulsion system represents a significant leap forward in rocket technology. This innovative approach offers numerous advantages over traditional propulsion systems, including increased efficiency, sustainability, and precision. Throughout this essay, we've explored the foundational concepts behind the propulsion system, the experimental setup, and the methodology used in testing. The observed results were promising, demonstrating the system's potential to generate thrust effectively. We also discussed the challenges faced and the solutions developed to overcome them. The future implications of this technology are profound. It could revolutionize the way we approach space exploration, making missions more economically viable and environmentally sustainable. The precision control offered by the system could enhance the success of satellite deployments and deep space missions. As we continue to refine and optimize this propulsion system, we move closer to realizing its full potential. The journey of innovation and discovery in rocket science is ongoing, and this breakthrough represents an exciting chapter in that journey.